Right. So what is the initiation?
When you make a radical?
Often it is. More generally, it just means that we form some active species that is involved in propagation. Very often, though, it is that you make a radical. And what's propagation?
When an active and a not active.
Right. It's the reaction of an active species with a reactant or product. More generally, it just means, like he said, the reaction of some active species with something that's not an active species. But what has to be true? What does it have to form? It has to form another active species. So looking back at that first example, what's our active species? A star. Did the second reaction form an A star? No, that's why it was not a chain reaction, right? It's a one-off. You make an active species, it reacts, it makes a product. Done. It's only a chain reaction if this step is making an active species. In other words, there's no net consumption of active species, like radicals. And then termination.
Two active species?
Yeah. We'll just say, often it is the reaction of two active species to make one inactive species. But more generally, it's the deactivation of the active species. But that deactivation can come about in multiple ways. All right, let's look at an example that does use radicals as the active species. And this is in some ways related to your homework, but I'm not doing the homework problem on the board. The difference between the example I'm about to go over and the homework comes in terms of how many steps are included in the reaction mechanism. Is that clear? All right. Hydrogen plus bromine goes to hydrogen bromide. So again, this is the reaction mechanism you're going to see in the class. It's a different one in the homework, okay? Yeah, thank you. Believe, but do not guarantee, that in the homework the only difference is this step is also considered reversible. I think that's the difference. What is the initiation step? All of them. No. What's the initiation? I got to make an active from an inactive. What is the propagation step? Speak up. 2 and 3. There is nothing wrong with that. You can have more than one propagation step. That's fine. Notice that both of them start with an active species and produce an active species. So the number of radicals is preserved. That's what makes them both propagation steps. What is termination? It's not when you run out.
It's the opposite of the initiation.
The reverse of initiation. So this is the forward step of reaction 1 is initiation. The reverse step of reaction 1, which notice it is reversible, is termination. All right, any questions? Okay. Just to give you an idea of the magnitude of these chain reactions, okay? Using the real values for this system, if I have a single bromine radical, how many HBRs do you think we get? Notice that we start with one here, but then we end up with one again. So it can go through this cycle of 2 and 3 multiple times. So the correct answer is not 2. How many do you think we get? It depends on the rate constants, yeah. I'm saying in the real system. Guess. 10? 100? Anything higher? You get 10 to the 6th HBRs. So it goes through this cycle. Somebody said till you run out of hydrogen. That's probably not a bad way of thinking about it. Under typical conditions, it goes through this cycle 1,000,000 times.
Wait, what was the original question?
If I give you one radical, how many HBRs will it make? Because notice that if I give you one here, it makes one, and then that makes a second one, but it also regenerates itself. So it can go through that cycle multiple times. That's what is unique about chain reactions.
So where'd you get the 10 to 6?
I'm saying if you actually use the real values from the rate constant. I'm not saying you could have solved that right now.
So when the concentration of hydrogen gas gets low, does it terminate then at that point?
Yeah, no, I mean the concentration of hydrogen gas will have an impact because the competing reaction for Br star, or radical, is either that it finds another Br radical and deactivates, or that it runs into a hydrogen molecule. But at typical hydrogen conditions, that's how many times it'll turn over before that happens.
But it's not the same molecule that we go through the 2 steps now.
I didn't hear you.
Okay.
Yeah, no, it absolutely can be. That's the point. It doesn't have to be, but the point is that it makes a hydrogen radical. That hydrogen radical reacts with a bromine to make another. So you're right that chemically it's not the same, but the point is if I give you one, you'll get 1,000,000 HBRs. Okay, so what is the rate of HBR in terms of the other rates? What's forming HBR? R2 plus R3, which, right, I can write as K2 times what? Right? Okay, what species do you think I can use PSSA to eliminate? Both radicals, yes. I'm going to use to eliminate so I can write the rate of Br is approximately equal to 0, right?
Why did you choose the radical?
They're active intermediates. They're present in very low concentrations. Those are 2 of the reasons why they make good candidates for PSSA. All right, so what is the rate of bromine?
R1 minus R2 plus R3. Oh, the Br dot. Right?
Sorry, yeah, I should have put that on there. Br dot, so what do I write? 2 times R1. Why is it 2 times R1?
So, what do the termination steps involves 2 hydrogen radicals colliding?
You can't. wouldn't it just feed right back into react with another bromine radical?
Yeah, that's the answer. You'd make a hydrogen molecule, but as long as there's bromine radicals around, it's not going to help you. The reason why it's not written the way, which I think might be your question, is why can't I just switch bromine and hydrogen? Is because hydrogen radicals aren't formed. They're way, way, way too unstable. So the actual reaction, this reaction, occurs via the mechanism I wrote. You actually do make the bromine radicals. You will never make a hydrogen radical. I mean, not at any conditions of a chemical reaction. But remember that I told you this reaction mechanism. If I were to ask you to derive a reaction mechanism, the big things would be, is it consistent with the observations that you have? So if I tell you it's first order or second order or something like that, or I give you rate data that's first order or second order, the reaction mechanism you derive should match the observables. The second thing on that list of is it a good reaction mechanism is it chemically feasible? So that goes to your question. Making hydrogen radicals is generally not very chemically feasible by just a hydrogen simply decomposing the way that the bromine can. Yeah?
Could it then just be a irreversible reaction of two hydrogen radicals colliding?
Sure. Yeah, that could be an additional reaction that you could write.
So wouldn't that also be terminated?
Yeah, that would then be a termination. But the reason why it's not there is simply because it doesn't really happen. Because the number of hydrogen radicals you form is diminishingly small. So the odds of two of them reacting with another is very small as well. But yeah, you can expand the reaction mechanism to include that. Okay, so 2 times R1, everybody knows why there's a 2. All right. And then what is consuming, well, I guess we can finish off, what else is forming Br? Radical. R3, and then what's consuming it?
Minus 2R1.
Minus 2 R1
2 times R1 and
Plus R3. We're gonna leave there, so that.
what else consumes Br dot?
Minus R2.
We have two twos.
It's all minus
minus 1.
Yeah, sorry. So notice that all I've done is look at the reactions and I've multiplied them by the stoichiometric coefficients, right? Positive 2 for reaction 1, negative 2 for the reverse, positive 1 for reaction 3, negative 1 for reaction 2. If we were to continue with the idea of having the hydrogen radicals in there, it would just be 0 times R4. You would never write it down because what would be the point? But understand that it's just stoichiometric coefficients times the rate equations for each elementary step. I was just erasing the 0 times R4. All right, what about H dot? R2 forms it. Minus R3. And we're also going to set that equal to 0, right? So to make our lives a little bit easier when it comes to the algebra, we're going to go ahead and combine these two. This doesn't affect your final solution. This is just making the algebra a little bit easier. Yeah.
Are you making it equal to 0 because there's no accumulation? Or
Yeah,
basically-
that's the PSSA, right? Is it saying that the accumulation is negligible?
Okay.
So if that's equal to 0, what simplifies when I sum these two together? R3 cancels, what else? R2 cancels. That's why it makes the algebra easier. Look for things like that when you're on, in an exam situation, right? Sometimes you can do little tricks that make the math much faster. So what am I left with? I'm left with, and I'm going to go ahead and substitute things in now, 2 times K1 times BR2 minus 2 times K minus 1 times BR dot squared. And again, that's approximately 0. Why is it squared? Right. Why do I put the 2 in front of the rate constant, and sometimes I put it in the exponent? So, maybe it wasn't a good question to the class. This is a collision, right? This is 2 BR radicals coming together. So the probability of them coming together is proportional to not twice their number, but their number squared. Okay? It's how much of one do you have times how much of a second one do you have. So it's a squared term, not simply twice the number. Twice the number comes from when I'm adding up all the rates, and I simply have to account for the rate of reaction 1. You know, every time I do reaction 1, I make 2 radicals. So don't be thrown by where the 2's are. They have totally different reasons for being there. And that's why it's here, even though this is not squared. The 2 is still there. Right? And here it's in both places. They have totally different reasons. They are both the stoichiometric coefficients, but the reasons why they're written are different. All right, so if we rearrange that to get BR dot, what we get is 2 times K1 over 2 times K minus 1. Those obviously cancel. You get bromine. This whole thing is to the half order. Everybody see that?
You assume it's positive?
I assume it's positive.
Yeah, when you take the square root, it's plus or minus, right?
Yeah, so yes.
Okay.
Can I have a minus concentration of something?
No.
No. So yes, it's the positive root of this. What is this?
Big K1.
Big K to the 1/2 times. So, is step 1 quasi-equilibrated? Yes, it is. Because I was lucky enough to be able to write it just like that. Yes.
You wrote the rate of BR radical formation and the rate of hydrogen radical formation. You didn't account for the hydrogen radical formation terms in your expression.
They cancel out when you sum the 2 together. If you look at the rate of BR, it has in it R2 minus R2 plus R3. And if you write it has other terms. 2 times R1 minus 2 times R minus 1. Now I write this for the hydrogen radical, R2 minus R3. When I sum those 2 together to make 0, those both fell out. It's just a math trick that saves us a lot of time. Okay, now I have an expression for HBr, right? But that still doesn't really get me there, because if I look at the rate, I have an expression for the BR radical, but if I look at this, then I still need an expression for the hydrogen radical. So now I go back to the rate of formation of the hydrogen radical,